Resurrection of the dead. This is what a sufficiently large quantum computer could do if it was available. Hi, I'm Ruben Tech, and no, I'm not morphing into Elon Musk. This is not hyperbole. This is just theoretical physics. I say theoretical because you would have to have a sufficiently large quantum computer to do so. Right now, we don't know if we will be there. Today, I'm going to give you a quantum computing 101 course in under 5 minutes. I'm going to really try. I'm going to keep it super basic, but hopefully everyone will be able to understand. First, we got to talk about what is quantum physics. Basically, everything that you see in this world is determined by quantum physics as best as we know. That is our best description of reality. All other things such as Newton's laws, even Einstein's law of general relativity is considered classical mechanics. Okay? As far as we know, this system is quantum mechanical. This universe is quantum mechanical. And what that means is that everything you see in this picture, me, the trees, the grass, the river, all of it together, it's all a quantum system. And if you have some kind of magical machine where you could freeze time, all the properties that best describe that system perfectly are called, if you put them together, they're called state. Okay? So imagine that you've snapshot all of this in time. Okay? You could think of that as its quantum state. Okay? And all this is a mathematical object. I'm going to keep it real high level. Quantum state, mathematical object. It's a complex number, but that doesn't matter. Let's just say it's a number. And as we know, you know, even if you snapshot time, time moves on, right? And so you go from one state to the next. And that evolution of that state is described by the wave equation. So the wave function epsilon, then you have the wave equation, Schrodinger's equation. One state to the next. Okay. That's what Schrodinger's equation does. It's 100% deterministic. Not that that matters. Determinism doesn't matter when it comes to quantum computers, but I just want to bring that up. Okay, and what does that mean, 100% deterministic? It means that any future state, I can always come back to this state utilizing the Schrodinger equation, because actually going forward and backwards in time does not matter in quantum mechanics due to something called unitarity. But we're not going to worry about that. All we're going to worry about is the fact that everything you see in this universe is a quantum system. It has something called state. State is essentially just a number, okay? And the evolution of that state from one state to the next is described by the Schrodinger equation. Okay, now let's move on. Let's move on to quantum computers. When we look at quantum computers, what they do is they create state, okay? They can create state. However, we're going to get theoretical now. Jacob Bekenstein told us that in order to replicate, say you're looking at me. I'm 6 feet tall, roughly, okay? In order, 170 pounds. In order to replicate me, right, you would have to know my quantum state. Well, we can't know it precisely, but he says that we have an upper bound to what that number could be. And he determined that utilizing something called the Bekenstein bound. And it's actually not even differential equations, it's just algebra. And so basically you would just take a two-dimensional circle and its diameter would be my size. That's it. And if you saturate that bound with the black hole saturates the bound. And what that means is it's the maximum amount of information in that bound. It saturates it perfectly. Okay? Not only is my state in there, okay, but every single version of me is in there. Okay, so my state from 1 second to the next, 1 millisecond, whatever it was, nanosecond. But also anything else that could fit in that circle is also in there. Okay, understand it's an upper bound, meaning that every quantum system that could fit in that circle is in there. So now let's make that circle a little bigger. Let's make it 10 feet. It's a 10-foot black hole. Now the state for every single person who has ever existed, who has ever lived, is contained within their state information is contained within that circle. Okay? And every person who has never existed, all their state information is contained within that circle. And every object, every single physical object that you can imagine that exists or doesn't exist right now, is contained within that circle. As long as it can fit within that circle, its information is contained within that circle. So if I had a quantum computer that was 10 feet in diameter and it had the information density of a black hole, again, we're talking theoretically, it could literally resurrect every dead person, and it could bring to life every person who has not yet been born at every stage of their life. Okay? Does that make sense? It sounds crazy. Now, if you had a sufficiently large quantum computer, you could replicate the universe. Now, I'm going to explain this real quick. It doesn't have to be the size of the universe. Because remember what I just said earlier, that Bekenstein's bound is the upper bound for all states that would be in that 10-foot sphere. But what if you just want to replicate me? Well, somehow you could narrow down my range of my states, because obviously I'm not that much information. You would not need a computer 6 feet tall. You would not need a black hole computer 6 feet tall. It would be orders of magnitude smaller. Because myself, my states, all my possible states, it's only a small subset of that black hole's information bound. So, to replicate the universe, you would not need a quantum computer the size of the universe. Because a quantum computer the size of the universe wouldn't replicate just this universe, it would replicate all universes. Every single possible universe. It would represent the multiverse. Because remember, it is the upper bound. Every single possible state would be possible. So it would represent all universes. So all you'd have to do is somehow narrow down what we know about this universe, and you could replicate it in an order of magnitude smaller quantum computer. Okay? So when I say this, you might be like, why do I never hear about this? Scientists do not talk about this because we are nowhere even close to this. Okay? Our computers, remember at the beginning, I said they have to be sufficiently large. Right now, Google is in the lead by far. And their Willow chip, I can't remember off the top of my head, but I believe it's under 50 qubits. The largest quantum system out there is 500 qubits, but that doesn't matter because it has too much loss to air. Willow has the least amount of air, it's 50 qubits. It needs to be so much larger than that. It doesn't need to just be millions, it needs to be quadrillions of qubits. So right now, a lot of scientists do not believe we will have sufficiently large quantum computers, or they don't believe it will happen anytime soon. So that's the discussion that you hear. When you hear Sabina Hassenfelder, when you hear Dennis Hassabis, when you hear all these brilliant scientists talking about that, the question is, will these systems be able to scale to be able to help us anytime soon? The answer, honestly, is probably no. It's probably not going to happen in our lifetime, or at least not in my lifetime. Okay? But that doesn't mean that it cannot happen. So what they're talking about now is they're just like, hey, we can solve these equations, because people came up with algorithms with even smaller amount of qubits that you can do amazing things with. Okay? So that's what they're looking at now. So understand that when you hear about quantum computers, they're just talking about what's feasible now in the foreseeable future. Okay? But they're not talking about what is theoretically possible. Okay? And here's why I'm very optimistic. Because if they can string 1 million qubits together, then what's to stop them from stringing 10 million qubits together? What's to stop them from stringing 10 billion qubits together? We always know that technology only moves forward. It might not be in my lifetime, but just the thought of it being able to happen, to me, is absolutely amazing. So from now on, when you hear about quantum computers, understand that the discussion that the physicists are having is just on how useful are they going to be to us now in the near future within 20, 30 years. They're not discussing the potential that they have. If you went to any physicist, including Sabina Hasselfelder, who's pretty negative on the topic, and you said, hey, I have a quantum computer, theoretically, imagine I have a quantum computer, right, with the density of the moon, the size and density of the moon, right? I have a black hole quantum computer the size of the moon. What could I do? And I guarantee you, she will tell you, you could do literally, virtually anything. I mean, I don't know if that'd be large enough to replicate the universe, this instance of the universe, but it would be pretty darn close. Okay? So that, when I say quantum computing is like the even greater than the invention of fire, that's why I say that. Because it's very possible in a couple hundred years that I could be resurrected, you could be resurrected through quantum computing, right? I mean, you would need leaps and bounds. Maybe, like nowadays, you would have to think maybe a timeline would be like 400 years. I don't know. It's hard to say how fast technology goes. Okay, 11 minutes, 30 seconds. That's a little long. Hopefully you understand everything. Everything is a quantum system. Every quantum system has something called state. State describes the system perfectly. It's a mathematical object called epsilon, right? The wave function, the evolution of the state from one state to the next is 100% deterministic. Schrodinger equation, okay? And a quantum computer can emulate these states perfectly, perfectly. It just has to be sufficiently large enough, which it is not, to do anything amazing like I was saying right now and not in the near future that we can see. But maybe one day it will be. That's it. Have a great day.